Optimization example 1. A square piece of cardboard 40 centimeters by 40 centimeters has 4 corners removed as shown, and we can see that the corners are x by x squares. The flaps are then folded to produce a box. Find the dimensions of the box that maximize the volume. Obviously this is going to be an open box because there's no top if we just fold the flaps up. So, well, let's consider this diagram down here. When we fold along these lines here, this edge of the box must be 40 take away 2x. So this one is 40 minus 2x. And we can apply the same argument down this side. So 40 take away the 2x would be this length here. And then the height of the box would be x once you fold that flap up. So the volume is going to be x multiplied by 40 minus 2x multiplied by 40 minus 2x. So that's going to be, well, 40 times 40 is 1,600. Then we've got take away 80, so let's take away 160x plus 4x squared. So that's going to be 1,600x minus 160x squared plus 4x cubed. Now we want to find the value of x that gives us the maximum volume. So let's go for dV/dx. So it's going to be 1,600, take away 320x plus 12x squared. So we want 12x squared minus 320x plus 1,600 to be equal to 0. Now just looking at that, I'm not sure that I can factorize it, so what I'm going to do is use the quadratic formula. So I'm going to say x is 320 plus or minus the square root of 320 squared, take away 4 times 12 times 1,600, all divided by 24. So the first thing to do there is work out what's under the square root. So 320 squared, take away 4 times 12 times 1,600 gives me 25,600. So x is going to be 320 plus or minus the square root of 25,600, all divided by 24. So let's see what values of x we get there. So what have we got? So, oops, look at that. So we've got 320 plus the square root 25600 all over 24. And that actually gives me 20. Oh, I might have been able to factorize this. So that gives me 20. And now we need to try the negative root. So we'll just go back and change that plus there into a minus, and let's see what that gives me. It gives me 20 over 3, which is 6 2/3. So 6 2/3. Now, we could use second derivative to find which is a max and which is a min, but we don't need to here. If our flap was 20, we'd end up with no cardboard. If that was 20 along there, and that was 20 to there, we'd actually be cutting every single bit of the cardboard away. So we don't want the 20, it must be the 6 2/3. So then we need 40, take away twice the 6 2/3. Remember 6 2/3 was 20/3. So that's going to be 40 take away 40/3, which is 120/3 take away 40/3, which is 80/3. So our box is going to be 80/3 times 80/3 for the base, and then the height is going to be the 6 2/3, which was 20/3. And those are our dimensions.